let me just quickly explain what this whole topic of Graph Studio, Graph Databases, Graph Analytics is all about in the first place. So if you haven't been looking into graph technologies yet, graphs are a very elegant and increasingly popular way to help you analyze data, and specifically analyze the kind of data which is heavy on the relationship side. So one typical example for that would be social networks. So a network in which you would represent people as vertices in the graph and connections between the people as edges in the graph. By means of graph analysis, you can easily identify people with many connections. Now, you can do that with relational technologies as well, but graphs are particularly good at also looking at, for example, people who are connected to people who in turn have many connections, or even more so at determining communities of people where the community is more interconnected than, connected to the rest of the world. Or looking at people who are sitting between two communities, or outliers, or finding paths between communities. This is what graph analytics is all about. It's nothing to do with graphs in the sense of bar charts or pie charts or the like. But when I'm referring to graphs, this is what I mean. Graphs in the world of analytics have been a very popular topic for the last number of years. It's been graph analytics has been among the top 10 technical trends in data and analytics as proposed by Gartner for at least 3 years in a row. And analysts such as Gartner are predicting huge growth rates. And that is actually also reflected in our customer base. I mean, I'm seeing a significant number of customers complementing their data warehouse, complementing their traditional analytics, sometimes even complementing their machine learning technologies with graph analytics, because graphs are just very good at analyzing indirect relationships, analyzing any kind of connectivity in complex interconnected scenarios. Now, just to give a little bit of background on what graphs are all about, graphs go way beyond social networks. They can be used to represent essentially anything. You could, for example, have a graph model where, like on the right-hand side here, you would have a customer who has purchased a product A, and that product A is manufactured by company B and is part of a promotion F, which is managed by a marketing agency D. And so you have all these different kinds of vertices, unlike the social network where you would primarily have people as vertices. You can model anything as a vertex and any relationship between these entities as edges. Right, so that's not only suitable for social networks or physical networks for that matter, but you can use that in a very elegant way, for example, to describe part hierarchies, or if you want to represent data lineage, or if you have a GDPR data repository and you want to find indirect connections to figure out which user has access to personally identifiable information in some application. Or finally, you could use that also to represent knowledge by connecting pieces of information, like in the public safety use case, where you could have a suspect C which owns a weapon A, and that weapon A was involved or was used for a crime F, and you could all model these kinds of relationships as a graph as well. And the one advantage that makes graphs so popular is that it is very easy to do the modeling. So I assume you all come from a relational background where, you would normally do your entity relationship modeling up front. You do all your third normal form analysis and all of that. That's not necessary here. You just get started. You create a couple of vertices and connections between them. If you want to add a new type of vertex, you could just add that. And that doesn't break anything. Same thing with relationships, or you add a new property to a given vertex. All of that is possible. There is no fixed predefined schema, and you can extend things as you go along. Obviously, that puts a certain amount of load on the application, and that it needs to make sense of all the properties, vertices, and so forth. It's this kind of schema on read type of approach. But for modeling, of course, it is very simple. And already from graphically representing the graph, visually representing the graph, you can derive information. The key thing, though, the main aspect why graphs have become so popular is that you can run all kinds of analyses which are specifically suitable for relationships, indirect relationships, and so on, like friend of a friend or connectivity. Is there a path between two given vertices and so forth? And the reason why graph databases are so good at that is that unlike in the relational world, in the graph database, you would explicitly store the relationship as a first-class object in the database. Increasingly, as I mentioned initially, people are also looking at how they can use these graph techniques to extend machine learning. For example, taking into account indirect relationships as a variable, as a additional feature which goes into your machine learning platform, and I'll have an example a little later on. Typically, what our customers are doing with these technologies is they use it for the purpose of community detection or influencer analysis, particularly in the context of targeted marketing. So if you look at what our customer Caixa Bank is doing, is that they have a huge graph which consists of all their customers, all the accounts, all the credit cards, all the locations where people live, and so forth. And from that huge network, they try to figure out which customers are related to which other customers, and using customers they know a lot about to infer information for those customers which are either new or where they don't have that much information, just by looking at the social interactions or the interactions as a whole, trying to figure out what kind of customer is it that I'm currently looking at. That's one of the typical customer 360 type of applications. And sort of related to that, they can then use it for the purpose of product recommendation. Now, that's another important class of applications which we're seeing in graph analysis, looking at similar behavioral patterns in customers, maybe customers purchasing similar sets of products, and so looking at things where behavior is similar. And if you look at things which are similar, you can also, of course, use that technique to determine which customers are particularly different, which brings us to the topic of anomaly detection, where we're using or seeing customers using our technologies for the purpose, for example, of fraud detection in healthcare, just to give you one example. What most of our customers are using graph analytics for is anything to do with path analysis and reachability. So be it in the context of data lineage, looking at how data flows through a set of systems, or looking at GDPR compliance, which user with access to which role has got which privileges on which BI dashboard, which in turn sits on which view, which sits on top of which table, which again has a column with, let's say, personally identifiable information, so that there is an indirect relationship between the user and that specific column, which you can determine very easily using these techniques. And finally, we have a number of customers in either anti-money laundering or tax fraud analysis, where they're using pattern matching in particular as part of the system. So that's the typical high-level use cases. Essentially, the techniques, the graph analysis is being used for two categories of analytics. On the one hand, customers would use what we call query processing, which is the interactive search on a graph network. So if you imagine this to be a set of bank accounts, like the ones here on the left-hand side, so bank accounts which are interconnected through financial transfers between them, right? And you have maybe a suspicious bank account in the fraud department. People would look at a given bank account and the direct connections, so the ones which are connected through financial transfers with that fraudulent bank account, and then look at a wider scope of how's that indirect bank account connected to a third bank account, or both that bank account, and so looking at the entire network of things. That's the interactive, mostly query processing, looking at environments of given vertices, looking at property paths, doing pattern matching, and so forth. The one class of applications. The other class of application is running graph algorithms. So essentially executing algorithms from graph theory, which allow you to determine the importance of a vertex or of vertices in general, finding a metric that reflects the importance of a vertex, or which detects communities, clusters, which generally evaluates the structure of a graph or figures out shortest paths between two given vertices. These are the two classes of applications, and in our technologies, those of you who haven't seen our on-premises product, in our technologies, we support both of these classes of applications. For example, you could use the graph algorithms which we're providing with the product to figure out the importance of vertices in a given network, and then use PGQL, the property graph query language, to extract those vertices which are particularly important, and then the neighboring vertices, for example. So you could, for example, have a query which extracts all vertices which are up to 3 hops away from a given central node, which is the most important one, for example, which has a metric of 5 in this case, and then look at all the indirect relationships. Now, if you want to do this kind of pattern matching query, you would need a pattern matching query language, because obviously SQL has no way of directly expressing this yet. We're working towards a standard which does this. There is the SQL PGQ standardization effort currently underway, but for the time being, SQL does not allow you to specify these kinds of patterns, which is why we have proposed our property graph query language for the standard, property graph query language, so PGQL. And to give you a feeling for what this query language looks like and how it works, here's a simple example at the top, which basically says, find me all people, all vertices of type person, which are connected through a likes relationship, which is a directed relationship, as you can see from this arrow, to another vertex of type person, and with the additional predicate that on the initial vertex M of type person, the property name equals Mario. So we're essentially looking for all vertices of type person which are connected to Mario through a likes relationship, right? Anything which is associated with a vertex is in parentheses. Anything which is associated with an edge is represented by these square brackets. And as they are, they can potentially be directed relationships, you would have this arrow. So this looks pretty much like SQL. Right? You have a select from where, you've order by, you've got group by, all of that. But in order to be able to express a graph pattern, we have this specific match clause. Now, obviously, this simple query is something you can easily express in SQL as well. But if we take the second query here, it's already getting a little more complicated. Like in SQL, we have the possibility to specify a path. In this case, we're defining path as has parent as some vertex, any type, which is connected through either a has father or a has mother relationship, again, directed relationship, to a vertex of type person. That would be the path. And then using this path, we can then specify indirect relationships of one or more hops. So what this query means here, what it says is we're trying to find all common ancestors, or to be precise, we're trying to find the name of all common names of all common ancestors using the following match query. We're looking for people, so vertices of type person, where P1 name is Mario and P2 name is Luigi, which are connected through a has parent relationship of one or more hops to a vertex variable ancestor, and that vertex variable is the same in both match parts, so that we're looking for the common ancestors. Now, again, you could represent this in SQL, but it would be significantly more. I mean, I don't know about you, but I've always been struggling with the connect by prior clause, and I mean, these days we would use recursive with statements for this purpose, but still you sort of easily end up with a fairly complex query, and this match clause is just very powerful in representing these kinds of indirect relationships, particularly like in the case here, if it's multi-hop relationships. So this would be the pattern matching query language, and as I said, besides the pattern matching query language, we have a large number of algorithms from graph theory, which we provide with the product, which allow you to do community detection, influencer analysis, ranking and walking. You can use those to evaluate the structure of your graph, or determine whether there is a connection, or the shortest connection, or the fattest path, or whatever between given vertices. Plus, there's a number of specific algorithms like the WTF algorithm, which is not what you think it is, but it's what Twitter uses for who to follow algorithm. Or we have a number of machine learning algorithms which we have just made available in the production version of our on-premises product. These are the algorithms which we provide with the product, and have been providing with the product ever since we launched the product, which was back in 2016. Quick remark here, as I said, just launched the latest version, the latest release of the on-premise product, which is version 21.1, which has these machine learning algorithms. These are not yet enabled in Graph Studio on Autonomous Database, just so that there's no confusion around this. This is, for the time being, just available on premises. But, it's part of the set of 60-odd algorithms which we provide as part of the product. All of these algorithms are available or are executed in memory on dedicated in-memory data structures, and they are parallelized to the degree that they can be parallelized. So that is essentially what makes it a very powerful analytics product. And it has been used as such, as I said, for years, because we've launched it many years ago. Which brings us to the next topic, which is Graph Studio in Autonomous Database, finally. But before we come to that, the on-premises product, as I said, has been around for years. That is something which you could use on premises, or you could use it on the Oracle Cloud. We've made it available as a marketplace image a long time ago. So no matter what, you can use it either on premises or on the Oracle Cloud, independent of Graph Studio. However, if you want to do that, right, you would either download and install the environment, or you would, install the OCI marketplace image, and then you would need to create your graph from your relational data if you have relational data, or load your native graph file formats. You would want to use some kind of analysis environment, like either a Python client or a Java shell or a notebook environment, some visualization, and then you would need to operate and maintain this complete environment. And in order to make that easy for you, or easier for our customers altogether, particularly for you with your focus on the autonomous database, we have launched Graph Studio as an additional tool in the autonomous database, as a self-service graph database and analytics environment, which essentially uses the autonomous data warehouse as the storage infrastructure underneath, but which is also not only using that infrastructure which we manage for you, but we would also manage the complete tooling and environment for you. So all the self-driving, self-securing, self-repairing capabilities of the underlying database extend to the complete graph analytics environment, which in turn includes a modeling tool to map relational data to graphs. It includes a notebook environment, which you can use for interactive analysis, for collaborating with other analysts and so on, and has visualization capabilities built in. And all of that is sitting on top of the proven graph server, the graph analytics engine, which we have been providing for years. Right. With Graph Studio, what we're covering is the entire workflow, the entire analytics workflow, which you would need to address with Graph Analytics. So we are providing a tool for the first step, which is to build and model a graph, to essentially take your relational data and map them to a graph. And I'll show you what that looks like in a moment. Then next step, how to prepare your graph, enhance or enrich your graph, gather additional information to complete your graph, run the algorithms, move them into the in-memory data structures, the dedicated in-memory data structures, and then collaborate with your co-workers, share the results of your analysis in notebook environment, and then move once you have a sort of end-to-end flow, move this end-to-end flow into a production workflow. That complete workflow we are addressing with Graph Studio. And Graph Studio, just to clarify that, is currently, as I said, not only available on as a limited availability service, but it is also and will for the foreseeable future only be available on the autonomous database, meaning it will not be an on-premises product. It is, or not, at least not for the time being, right? It's it is deeply integrated with the Oracle Cloud infrastructure. So for the time being, we will only be making it available on the autonomous database. Right. So going through that workflow, just to give you an idea of how Graph Studio works and how you would perform analysis, assuming that you're starting with a relational data model as a first step. What you would need to do is to take your relational model and then designate what becomes a vertex and what becomes an edge. And we are providing a little tool called the Graph Modeler, which helps you to perform this very step, which essentially looks at your relational data model, looks at the tables, looks at the primary key, foreign key relationships, and then suggests a first cut model, which you would then, or which you can then either use or refine as you go along. Because unlike in the relational world, where you would essentially have a mathematical sound theory that defines your complete data model, here you're very free in what you map to a vertex, or whether you want to just reflect things as a property maybe, and so forth. And it is not at all uncommon to modify the data model as you go along, because the graph model essentially depends on the kind of analysis which you want to perform on the model. Right now, I've been, talking about all this theory. Let's see that we show this in practice. Let's see if my environment is still alive or whether it's gone to sleep yet. Let me see. Here we are. Okay, so when you log on to the autonomous database, you will find. Let's see if that is still up and running, or whether I have logged out in the meantime. It's probably no, we're still there. So if you have your autonomous data warehouse, which you all know and love, if you're enabled for Graph Analytics, under the Tools section, you will find Graph Studio, and that is your entry point into the Graph world. In order to use it, you need to have the appropriate privileges, but assume you have them. When you need to create a user, you need to assign the appropriate privileges. When you have them, kick off Graph Studio. This is what you see. And it essentially consists of two parts. You have the modeling piece and you have the analysis piece. There's a little bit of administration around it, but these are the two main things. And if we look at the modeling to start with, just to give you an idea, let's use, say, the sales history schema, which I assume most of you will be familiar with, because it's the demo schema which we provide with most of our, especially the data warehouses as sample data. If we take the different tables in the sales history schema, that would be the fact table, the sales table, and a couple of other tables, and we use these and have the graph modeler suggest a target data model. It would look at the different tables. It would look at the primary key, foreign key relationships, and then on the basis of that would say, okay, it looks like it would make sense to have the fact table as a vertex. It would make sense to have all the other tables which I've selected as vertices, and all the primary key foreign key relationships would show up as edges, and the tables would have, the vertices would have the following properties. It has a label and so forth. If you want to graphically represent it, this is essentially what it would look like, right? You would see you have the fact table here, or what used to be the fact table here, and you would have what used to be the different dimensions hanging off the fact table as vertices in the graph. Right? That's what the modeler suggests. Let me quickly show you that the modeler is actually pretty sophisticated, because if you, for example, let's select just the customer's products and the fact table, which is then essentially just an end-to-end relationship between customers and products, with the sales table being the intermediate table. If you take that, the modeler will see, hang on, this is just an end-to-end relationship. So essentially, we can model that as products as a vertex, as vertices, customers as vertices, and the fact table could actually be represented as edges. So it would simply look like this, right? You'd have the products and the customers connected through the sales relationship, right? You could then go and modify that and say, okay, I'd rather have it the other way around and use purchased as a label, just to take that as an example. And then it would look like this. You have customers and they purchase products. And what this thing does under the covers is it generates what we call a PGQL DDL statement, which says create property graph. And that property graph consists of vertices, which come from the following tables with keys and properties and so on, and edges, which come, in this case, from one table, which take the source from the customer's table, and the destination is the product table. And That's the label, and it's got some properties and so on. So that is essentially what it means when I say you are mapping relational data to a graph. Okay, in the interest of time, I'm going to stop this here. For the next part, actually, what I wanted to use is another graph for the demo, which is a little more simple, which consists of bank accounts, which every vertex is a bank account, and the edges between them are banking transactions, which come from a individual table. Right, it's not a huge data set. It's 1,000 vertices, 5,000 edges, and so on. What you can already see here is that in this admin page, it says it is in memory, meaning we have moved the tabular data into the in-memory data structures. And what that refers to is what you can see. Yeah, okay, we've gone over the demos, so you've seen that. Is what we have here. That's the next step, where once we have taken the data from the database tables and we have mapped them to the graph model, what happens is that in the autonomous database, we are materializing all the vertices and all the edges in the autonomous database. Right? So you end up with one table which has all the edges, one table which has all the vertices. These are regular tables, which you can then modify. So you can just use plain SQL, bulk load into these tables if you want. You can merge the information with other data and so on. And that gives the model we're using here gives you the schema independence, because you can add new vertices, new vertex types, new properties per vertex, and so forth. But in order to run the analytics efficiently, what you need to do is move them into dedicated data structures where you materialize or you use the materialized edge to perform fast traversal queries, fast community detection algorithms, and so forth. So that would be the second step, which takes the content from the data from the raw tables here into in-memory data structures in order to efficiently run these graph algorithms. Right? And running these algorithms can, as I said previously, can mean executing community detection, ranking and walking, all of the things which I already talked about. Just to give you one example, if we take this little sample graph here, and again, the vertices here maybe represent bank accounts, and the connections between them are financial transfers, then if, let's say, you have identified a set of fraudulent accounts, like the 5 accounts here, and you're trying to figure out, okay, which accounts outside of the starting set are relatively close to these 5 fraudulent accounts, that they are bearing an increased risk that they're also involved in the fraudulent activity, then you could use an algorithm, in this case, an algorithm which gives you the relative distance, or you can also say closeness, of these additional accounts to the starting set, to give you a metric which helps you to determine, okay, which ones are closer and which ones are further away. Right? Looking at this set of whatever it is, a dozen or so bank accounts, it is relatively obvious that these 3 accounts up here have many connections to the starting set, so they are close in the sense of a graph, while that one down here is sort of many hops away and maybe not so risky. But try that on 3 months worth of transactions data at an average retail bank. That'll give you a little bit of a headache because it's just huge amounts of data. And using graph algorithms like personalized PageRank in this case to determine which accounts are close, in the graph sense, close to the starting set, can be a very powerful metric to help you to determine a metric for risk. Right? And then once you've run these algorithms, then you can use a notebook-based environment for further analysis, for interactive analysis, for documentation of your work, for visualization of the results, and so on. And this notebook-based environment, I don't know if you're using notebooks, otherwise already anyway, this notebook-based environment is what we're also providing as part of Graph Studio. And again, rather than going through this in theory, let me try to show you what this looks like in practice. We have a number of sample notebooks which we provide with the with Graph Studio. And just in case you haven't been looking into notebooks a whole lot so far, essentially, so that's a a single page application, browser based, which is divided up into paragraphs. Like this would be a paragraph, that would be a paragraph, and so on. And for each paragraph, you have an interpreter. So in this case, the interpreter here is MD, which stands for Markdown. So this first paragraph essentially is just for documentation purposes, because it renders the text which is presented in Markdown here as HTML. So if I run this is not particularly sophisticated because it just renders HTML, nothing else. But it's useful for documentation. It's got a heading. So this is the sample notebook for PGQL PGX paragraphs. And what we're showing here is the following 5 things. Like we're querying a bank graph just to visualize 100 elements, and then we look at the top 10 accounts and so on and so forth. And just to show you briefly what this looks like, this is a typical simple PGQL query, which just essentially takes 100 objects from the graph called bank_graph, where we have a vertex S, which is connected through a relationship T to a vertex D. This means in the bank graph, we have all these bank accounts. Every vertex is a bank account. We have S would be the source vertex. These are the blue ones, which are connected through a financial transfer to the D vertex, which are the green ones, which are the destination vertices. And if you look at the simple graph here, right, you would see a source vertex. This one is connected to an orange one, which is at the same time a source and a destination, which in turn is connected to that one, and so forth. And you can now move around the graph. You can zoom in, look at things more closely, and so on, or you could find other ways of graphically representing the graph. For example, we show that in concentric circles. This looks a bit different, right? This is what it looks like in the overview. And then again, you can drill down. You can analyze individual accounts. You can do further tricks on the visualization and highlight specific aspects and so forth. Again, in the interest of time, I'm not going to go into all of the details, but just to give you an idea of the kind of interactivity which is possible. This is just taking an arbitrary set of 100 accounts from, 100 objects, accounts and transactions from the graph store. And then if we want to run analysis, maybe it's interesting to figure out, okay, which account has mainly deposits. That would be sort of a PGQL query, which gives you numeric results. That's obviously also possible. I think you can already see, 934. Well, it's got a number of deposits, so that's a very active account. Let's look at that in more detail. And just for the sake of the example, let's try to figure out if account number 934, is involved in circular payments. Now, if you think about circular payments, you start at a given account, in this case 934. You go to through 1, 2, 3, 4, 5 transfers, ending up at 934. That looks like money laundering, right? Just things starting at one account, ending at the same account, going through a number of steps. That's odd. This would be what this kind of circular query or circular payment analysis would look like, right? We have a vertex A, which is connected through 5 transfers to itself. And in this case, the account ID on A is 934. If we graphically represent that, that's not terribly exciting because it just says, okay, here's 934. And yes, there are connections of 5 hops, one or more, from 934 to 934. If, in order to make that graphically a little more appealing, if we want to look at, okay, here's 934, let's look at the last step in the chain. So we start with 934, we do 4 transactions, and then the 5th transfer is this one back to 934. This is the kind of analysis we can do here. In PGQL terms, this would be, you start with A, you do 4 transfers to a destination vertex D, and then the final 5th transfer back to A, and then we're representing D here, or vertices of type D are these, all right, these ones. That is what you would see here. And then you could take that one step further. You can look for 6 hops transactions. And then if you want to visualize the entire chain, you can also do that, except the match clause becomes a little more complicated because then you need to explicitly name every intermediate step. But you can do that. And then again, you could zoom in, you could look at things, you could, in order to give it a little more screen estate, you could also expand this and render this in sort of all kinds of interactive ways. Just to give you an idea, again, you could play around with the labeling, you could play around with the different kinds of graphical representation and so forth. Right, so we've got 5 minutes left. Quick summary. Hope I've given you a bit of an idea of what graph databases are in the first place, what they can be used for. Hope it's become clear that they are particularly useful for any kind of analysis where relationships, indirect relationships, or technically speaking, graph topology plays a role and provides new insights into these relationships, dependencies, behavioral patterns, and so forth. Can use them very nicely in conjunction with machine learning, generating a metric which could feed into the machine learning platform as an additional feature, for instance. Is a customer part of a given of a community, or is there a fraudulent pattern? Is there a fraudulent account up to 3, 4, 5 hops away from a given account? That could feed into the machine learning platform. Graph Studio as an environment. I hope it's become clear that we're offering that on top of the autonomous database, and for the time being only on top of the autonomous database, to provide end-to-end tooling. So modeling relation data as a graph, managing your graph data in the graph store, querying the graphs using notebooks for any kind of visualization, analysis, and so forth, executing the graph algorithms, using PGQL as a pattern matching query. And as I said, all of that sits on top of the autonomous database. We are managing the complete environment for you, including Graph Studio and all the bits and pieces associated with it. And it uses all the great features of the autonomous database that you know and love. Here's a number of links which you may find useful to get started. Thanks for joining us today, and I wish you a wonderful day, evening, night, whatever, depending on where you are on this planet.